Welcome to the course on 3G and 4G wireless communication systems. In the last lecture, we completed our discussion, or we completed one part of our discussion on the RMS delay spread. We said the RMS delay spread is the interval of time over which the signal copies are received in the wireless communication channel, because there are not just there is not just one signal component, but there are several signal components corresponding to the direct path and the scattered paths. We said the delay spread is the interval over time over which these signal components are received. We also said in typical outdoor wireless communication channels, wireless communication systems, the delay spread sigma tau is approximately 1 to 3 microseconds. We also said that if I take the Fourier transform, if I look at the Fourier transform of the delay profile, I get the Fourier transform of the delay profile, that is h of f, and we define the coherence bandwidth as that bandwidth over which this frequency response is approximately flat. We said that is the coherence bandwidth of the wireless channel, that is the bandwidth over which the response of the channel delay profile is approximately flat. And more importantly, we said a very important thing about flat fading and frequency selective fading. We said if the bandwidth of the signal being transmitted is less than the coherence bandwidth, then the system and the channel is a flat fading channel. In this case, there is no distortion. However, if the signal bandwidth is greater than the coherence bandwidth, as in this case, when the signal bandwidth is greater than the coherence bandwidth, then there is attenuation at the edges, which implies that there is frequency selective distortion. Hence, if the signal bandwidth Bs is greater than the coherence bandwidth, there is frequency selective distortion. And lastly, we also said that the coherence bandwidth and the delay spread are inversely related to each other. That is, if the coherence bandwidth is high, then the delay spread is low, and similarly if the coherence bandwidth is low, the delay spread is high. And more specifically, an approximate relation between coherence bandwidth and delay spread is coherence bandwidth Bc is equal to 1 over 2 sigma tau. This is employed very frequently, and to a high degree of accuracy, this characterizes the relation between the coherence bandwidth and the delay spread sigma tau in a wireless communication system. Now, with that, let us go on to today's discussion, which is we were starting to explore the relationship between in the time domain between the coherence bandwidth and delay spread. What does it mean in the time domain? We looked at the frequency domain interpretation of this. Now, let us look at what is happening in the time domain. So, let us look at relation in time domain, and for that we said we will start by considering a signal which has symbols S0, so this is a digital communication signal. It has symbol S0, S1, S2, S3, S4. So, S0 is the first symbol, S1 is the second symbol, S2, S3, S4 are subsequent symbols that are being transmitted. Now, this is transmitted from the transmitter. What I receive at the receiver is one copy of this from the direct path between the transmitter and the receiver, and then I will receive another path from the scatter component. Let us say I have one direct path and one scattered component, then I will receive another path from the scattered component, which is slightly delayed with respect to this signal. That will look something like this. It is the same signal, except it is slightly attenuated and delayed compared to the original signal. So, that will look like S0, S1, S2, S3, S4. Look at this signal, look at the second signal, it is the same as the original signal. So, if this is received from the direct or line of sight path, this corresponds to the non line of sight path or the from the scattering. We said we receive multiple components of the transmitted signal, one from the direct path and several from the scatterers along the scatter paths, and the signals from the scattered components are delayed with respect to the line of sight signal. Look at this, it is exactly the same signal except it is slightly delayed, and this delay is nothing but the delay spread sigma tau of the system, and this interval of the signal is nothing but the symbol time of my transmitted digital communication signal. Alright. Now, look at this, I have a signal and a delayed copy arising from the scattering in the wireless channel. At the receiver, these signals, the direct component and the scattered component, are going to add up, and that is going to result in interference at the receiver. But look at this, when I add these two symbols up, because the delay is small, because sigma tau is small, when I add these symbols up, when I add these signals up, S0 interferes with S0, S1 interferes with S1, S2 interferes with F2, S2, that is the same symbol is interfering with each at each time instant, because sigma tau is very small. So, sigma tau is very small. More specifically, sigma tau is much smaller than T symbol, where T symbol is the duration of the digital communication symbol. So, I am saying when this delay spread sigma tau is less than T symbol, where T symbol is the time duration of the digital communication symbol, then at the receiver, because of multipath interference, the same symbol is interfering at every time instant, that is S0 is interfering with S0, S1 is interfering with S1, S2 is interfering with S2, S3 is interfering with S3, and so on. Now, let us consider a scenario in which the delay spread is much greater than the symbol time. Now, let us consider a scenario in which the delay spread is much greater or comparable to the symbol time. Let me write this as greater than symbol time. I have a signal that is received from the direct path that is S0, S1, S2, S3, S4 and so on. However, the second symbol here, second signal here is delayed significantly compared to the first one. So, this is my direct signal, this is my scattered signal, and look at the delay between these two signals. The delay between these two signals is now sigma tau, which is much larger than the symbol duration. Here I will have S of minus 1. So, I am saying I have a signal that I am receiving from the direct path or line of sight, and I have a delayed signal that is received from the non line of sight or the scatterers or the scattering in my 3G 4G wireless system. Now, when this signals interfere at the receiver, because this delay sigma tau is greater than the symbol time, look at this, S0 will add with S minus 1, S1 will interfere with S0, S2 will interfere with S1, S3 will interfere with S2. So, what is happening is the previous symbol is interfering with the current symbol. Look at this, in this case what I had was that S0 is interfering with S0, but in the previous case S0 was interfering with S0, S1 was interfering with S1, S2 was interfering with S2. However, In this case S0 is interfering with S minus 1, S1 is interfering with S0, S2 is interfering with S1, that is the previous symbol is interfering with the current symbol. Hence, this is resulting in what is known as inter symbol interference. Hence, when the delay spread is much smaller than the symbol time, there is no problem, there is no inter-symbol interference, but when the delay spread becomes larger than the symbol time, what happens is the past symbol interferes with the current symbol. In fact, if you have more signal copies and the delay spread is very large, then you have the second past symbol, that is S of minus 2 interfering with S of 0 and so on. So, as the delay spread increases, what happens is we will start having progressively worser and worser inter-symbol interference at the receiver. So, let me write this down clearly in this slide over here. Sigma tau, that is the delay spread, this is the delay spread is greater than, or let us say is much greater than the symbol time. This is the symbol time. This leads to nothing but this leads to ISI, or in other words inter symbol interference. So, the delay spread much larger than the symbol time leads to inter-symbol interference. Now, let us take this idea a little bit further. Sigma tau greater than T symbol, that is the symbol time, leads to inter-symbol interference, that is what we saw. Now, let us take the reciprocal of this. If I bring T symbol to the left hand side, sigma tau to the right hand side, I get 1 by T symbol is greater than 1 by sigma tau, which implies leads to inter-symbol interference. But now, look at this quantity 1 over T symbol. What is this quantity 1 over T symbol? This is nothing but the bandwidth of the signal. If I have a signal with symbol time T symbol, the bandwidth of the signal required is nothing but B signal, So, 1 over T symbol is nothing but the bandwidth of the signal. So, from your digital communication system theory, you know that if I have bandwidth Bs, the symbol time that is possible is 1 over Bs, and look at 1 over sigma tau. What is 1 over sigma tau? Remember, we said Bc equals 1 over 2 sigma tau. Hence, 1 over sigma tau is nothing but twice Bc. Hence, if Bs greater than twice Bc, that has inter-symbol interference. But look at this condition. What is this condition? Bs is greater than twice Bc. Remember, we looked at this condition before. Bs is greater than twice Bc implies Bs is greater than Bc. That is nothing but the condition for frequency selective distortion. So, Bs greater than Bc implies 1 over T sim greater than sigma 1 over sigma tau, implies sigma tau greater than T sim, implies ISI. So, if I follow the argument from here to here, what I get essentially is, let me write that down now, frequency selective distortion in frequency domain implies inter symbol and this is the surprising conclusion that we can derive, which is essentially that if I have frequency selective distortion in the frequency domain, that is if Bs is greater than Bc in the frequency domain, I will have frequency selective distortion, which means in the time domain that results in inter-symbol interference. Now, similarly, if I have Bs less than Bc, then in frequency domain it is a flat fading channel. In time domain it means there is no ISI or no inter-symbol interference. So, that is the beautiful conclusion or the very intuitive result that we can derive, that is frequency selective fading and inter-symbol interference are inherently related to each other, which means if the signal bandwidth is greater than the coherence bandwidth, what I will have is frequency selective distortion, which essentially means inter-symbol interference. Also, if Bs is greater than less than Bc, that is the signal bandwidth is less than the coherence bandwidth, then the channel is a flat fading, there is no distortion in frequency. In time also there is no ISI, no inter-symbol interference, which means no distortion in time also. So, these are two intuitively or inherently related ideas, and it is essentially very important in a 3G, 4G wireless communication system, in any wireless communication system, to understand that there is a very inherent and intuitive relationship between frequency selective fading in the frequency domain and inter-symbol interference in the time domain. Both of these are essentially the time and frequency domain analogues of each other or counterparts of each other. So, it is important to understand the relation between them. Now, let us do an example to sort of solidify our understanding of coherence bandwidth and frequency selective fading. So, let us do an example. We said outdoor channel, in an outdoor channel the delay spread, typical delay spread sigma tau is approximately of the order of microseconds, that is for outdoor channels the delay spread is approximately 1 microsecond. Now, let us compute the coherence bandwidth corresponding to this delay spread. Alright, we know that the coherence bandwidth Bc is 1 over 2 sigma tau, which is 1 over 2 times 1 microsecond. This is nothing but 1 over 2 microseconds, which is essentially 500 kilohertz. So, I am saying the coherence bandwidth in an outdoor 3G, 4G wireless communication channel is approximately 500 kilohertz. So, the coherence bandwidth is approximately 500 kilohertz. Now, let us compare it with our known communication systems. Let us look at GSM. GSM has a bandwidth of 200 kilohertz, roughly 200 kilohertz, which implies Bs equals 200 kilohertz. Now, remember coherence bandwidth is 500 kilohertz. So, Bs is less than Bc. Look at this, Bs is 200 kilohertz, Bc is 500 kilohertz, Bs is less than Bc, hence a GSM or a 2G wireless communication system. Remember, this is a 2G wireless communication system, this is a flat fading system, or this is also a system in which there is no ISI in GSM, because its bandwidth 200 kilohertz is much smaller than the coherence bandwidth, which is 500 kilohertz. Hence, this 2G wireless system is flat fading or there is no inter-symbol interference. Now, let us look at a 3G wireless system. Let us look at a WCDMA system. Remember, WCDMA is a 3G wireless system. In fact, it is a spread spectrum system, a wide band spread spectrum. It is a spread spectrum system, which means its bandwidth is huge. Its bandwidth is 5 megahertz, which is also can be written as 5000 kilohertz. All right, the bandwidth is 5 megahertz, each megahertz is 1000 kilohertz, so its bandwidth is 5000 kilohertz. This is BS WCDMA. Now, look at this is 5000 kilohertz, much greater than 500 kilohertz, which is the coherence bandwidth. So, BS for WCDMA is much greater than BC. So, BS is 5 megahertz, which is much greater than BC, which is 500 kilohertz. Hence, by definition, by our definition, this results in frequency selective fading in the frequency domain. In the time domain, there is going to be ISI or intersymbol interference, and this is a 3G system. So, the difference here essentially compared to a 2G system is because the bandwidth is higher, this bandwidth is much greater than the coherence bandwidth, hence resulting in frequency selective distortion and also ISI, which is bad in a wireless communication system, because now we have to employ some technique at the receiver, so that we can reverse this distortion. In the frequency domain, it is this technique that is employed to reverse this distortion is known as an equalizer, because the distortion is frequency selective. You have to equalize the frequency response at the receiver, that is known as an equalizer. However, we will not go in detail into the discussion of an equalizer, because that is relevant to the, or you should have studied that in your course on digital communication system. But here we will just note that when the distortion is frequency selective, when there is intersymbol interference, we will need an equalizer or equalization process at the receiver to undo this distortion. All right. So, with that we complete our discussion on the delay spread. I want to again point out that the delay spread, in summary, delay spread is an important parameter in a 3G 4G wireless communication system, because it characterizes that interval of time over which you are receiving copies starting from the direct component to the scatter components, and the delay spread is inherently related to the coherence bandwidth. As this delay increases, the coherence bandwidth decreases, and if the signal bandwidth is less than the coherence bandwidth, that is fine, it does not result in frequency distortion. But if the signal bandwidth is greater than the coherence bandwidth, then we have a problem that results in frequency selective distortion, and its counterpart in time is essentially intersymbol interference. If the signal bandwidth is greater than the coherence bandwidth, it results in intersymbol interference in time domain, which is bad, because symbols start interfering with one another, making detection impossible or detection erroneous at the receiver. Okay. Now, let us go to the other aspect of a wireless communication system, which is also important, which is the Doppler shift. This is Doppler, or essentially the Doppler shift. We know from a basic discussion of high school physics that Doppler shift is nothing but the apparent or the relative change in frequency because of relative motion between the transmitter and the receiver. So, here let me draw a base station in a wireless communication system, which is transmitting a signal. All right. Let me draw a signal. A base station is transmitting a signal, and there is a receiver which is moving with a velocity towards the base station. So, this is a base station which is transmitting a signal. So, this is a base station which is transmitting a signal. This is a mobile station which is moving towards the base station, or it can also be moving away from the base station, but the motion has to be relative. That is, this is the transmitter, this is the receiver. There is relative motion between these, that is, one is moving towards or away from the other. In fact, it can be a scenario in which the base station is also moving. That is a complicated scenario. It does not occur in a wireless cellular network, but it can pretty much occur, for instance, in a wireless sensor network or a mobile wireless ad hoc network in such scenarios. So, when there is relative motion between the transmitter and the receiver, this results in a change in the frequency that is received at the receiver, that is known as the Doppler shift. So, that let me write it down formally. The Doppler shift can, or the Doppler shift is the change in the frequency of the electromagnetic wave that is arising due to relative, the keyword here is relative motion between the transmitter and receiver. So, Doppler shift is nothing but the change in the frequency of the electromagnetic wave. As we said, it is the change in the frequency that is arising due to relative motion between the transmitter and the receiver. And if, for instance, let me draw a transmitter. If my transmitter is here and the receiver is here and the receiver is moving towards the transmitter, then the received frequency is higher, and if the receiver is moving away from the transmitter, then the received frequency is lower. Alright. So, if the motion is towards the transmitter, then the received frequency is higher. If the motion is away from the transmitter, then the received frequency is lower. Now, let us go into let us look at how to compute the Doppler frequency shift. So, now let us look at computation of the Doppler let us look at how to compute the Doppler shift. Let me consider a base station. Let me simply consider a transmitter which is transmitting to a mobile station, a base station which is transmitting to a mobile station, and this mobile station is moving at an angle of theta. Alright. So, this is my base station. Let me mark it clearly. This is my base station. This is my mobile station or my mobile terminal. This is moving such that if I look at the direction of the velocity and if I look at the line joining the base station and the mobile station, the angle between the velocity and the line joining the base station and mobile station is theta. So, this angle here is theta. Alright. Now, the Doppler shift Fd. So, the Doppler shift Fd in frequency Fd is given as Fd equals V cosine theta over C divided by V cosine theta divided by C into Fc, where V is the velocity, theta is the angle, C is the speed of light or the speed of electromagnetic wave in free space, we know that, and Fc is the carrier frequency. So, let me write down this. V is already indicated here, that is the velocity of the mobile terminal, theta is the angle between the velocity and line joining the mobile station and the base station, c equals speed of light, and Fc equals the carrier frequency. Alright, let us, and then the received frequency at the mobile is given as F, the received frequency is given as F receive is Fc, the carrier frequency, plus the shift, the Doppler shift, which is Fd, which is equal to Fc plus V cos theta over C times F c. Now, you can see from this, if 0 less than theta less than pi by 2, the mobile 0 less than theta less than pi by 2, then the mobile is moving towards the base station, which means cosine theta, if 0 less than theta less than pi by 2, ms is moving towards the Bs, and hence cosine theta is positive, because 0 less than theta less than pi by 2, cosine theta is positive, hence the frequency shift is positive or the received frequency is higher. Similarly, if pi by 2 less than equal to theta less than equal to pi, then the mobile is moving away from the base station. Cosine theta is negative for theta pi by 2 less than equal to theta less than pi, hence Fc minus something, hence the received frequency is lower. So, when the mobile is moving away from the base station, the received frequency is lower. That can be represented succinctly by this formula. In fact, you can see one thing very interesting, if theta equals pi by 2, look at this, if theta equals pi by 2, then cosine theta is 0, which means if the motion here is such that it is perpendicular to line joining the base station and the mobile, then cosine theta is 0, hence even though there is a velocity, there is no effect on the received frequency, is exactly the same. So, this says something very interesting, if theta equals pi by 2, even though there is a positive velocity, the received frequency is exactly the carrier frequency. So, as a function of theta, this is the received frequency at the mobile due to the Doppler shift. This is received frequency due to Doppler. All right. Okay. Now, let us do an example. Let us consider a carrier frequency Fc equals 1850 megahertz, and let us consider a vehicle moving at 60 miles per hour, vehicle moving at 60 miles per hour directly towards the base station. Which implies theta equals 0. So, what am I considering? I am considering Fc equals carrier frequency 1850 megahertz, a vehicle which has a person in it who has a mobile station, who is moving at 60 miles per hour directly towards the base station. We want to compute what is the Doppler shift. So, we want to compute Doppler shift and the received frequency. And we know that the Doppler shift Fd, so first let us look at this velocity. Velocity is 60 miles per hour. Let me convert this into standard meters per second. Each mile is roughly 1.61 kilometers. So, this is 60 into 1.61 kilometers per hour, which is equal to 60 into 1.61 into 5 divided by 18 meters per second, which is equal to 26.8 meters per second. So, 60 miles per hour is 26.8 meters per second. Let me write that down. 60 miles per hour equals 26.8 meters per second, which means now Fd equals V by C cosine theta into Fc, but theta equals 0. So, cosine theta equals 1. So, this is simply 26.8, that is the velocity, divided by 3 into 10 power 8, that is the velocity of light, into Fc, which is 1850 megahertz. Remember, we said the carrier frequency is 1850 megahertz. So, this is simply 1850 into 10 power 6. This is nothing but 165 hertz. So, the Doppler shift Fd equals 165 hertz, and the received Doppler frequency F received is Fc plus Fd, which is 1850 megahertz plus 165 hertz. Alright, so the Doppler shift we have calculated is 165 hertz, and the received frequency, because remember theta is 0, the mobile is moving directly towards the base station. So, the shift is positive. So, the received frequency is higher, it is 1850 megahertz plus 165 hertz. So, the Doppler shift is 165 megahertz compared to the carrier frequency, which is 1850. The Doppler shift is 165 hertz compared to the carrier frequency, which is 1850 megahertz. It might seem that this Doppler shift is very small compared to the frequency of the carrier, but we are going to see later that this small shift itself has a significant impact on the 3G 4G wireless communication system. We are going to look at this in either this lecture or the subsequent lecture, but this small shift will have a significant impact on the communication, on the wireless communication system. Now, let us go towards developing a model, try to understand this nature of the Doppler shift a bit more in depth. So, let us go back to our baseband. So, let us go back to our baseband channel. And we said that each path is characterized by AI delta t minus tau I, alright, where AI is the attenuation of the ith path, and tau I is the delay of the ith path. Now, consider a scenario in which, let us consider a scenario in which there is a mobile and it is moving directly towards the base station. So, there is a mobile, it is moving directly towards the base station. Now, let us say initially the delay of this is tau I, this path is the ith path, this has a delay tau I. Now, after t, let us say this is moving with a velocity v, after t the distance decreases by Vt. So, after t distance decreases by Vt, hence when the distance is decreases, the delay also decreases. Hence the delay of propagation on this path decreases by tau I minus Vt divided by C. Alright. So, as the distance is decreasing, the delay is also decreasing. Now, let us look at another case where this is the mobile station, this is the base station, and the mobile is moving at an angle of theta. The component of velocity in the line joining the mobile station and base station is v cosine theta. So, the velocity in this direction is v cosine theta. Hence, in a time t, the distance decreases, the delay decreases as tau I minus v cos theta into t, that is the decrease in the distance between the mobile station and the base station, divided by c. So, this is now the new delay. Let me write this tau I as a function of time. So, what am I saying? The delay, initial delay, this is tau I, which is the initial delay. However, this is not constant, because the mobile itself is moving with a velocity v with an angle theta. Hence, this delay is now changing with respect to time. How is this delay changing with respect to time? Tau I t, the delay at time t is tau I minus v cos theta t over c, where v is the velocity, theta is the angle of the velocity with the line joining the mobile and the base station. So, this is interesting. Now, we are saying that the delay of this channel is not constant, but on the other hand it is a function of time. Now, let us look at our earlier expression for the flat fading channel coefficient. So, remember the flat fading channel coefficient H, which is also the flat fading channel coefficient. Remember, this is given as I equals 0 to L minus 1 A I e power minus j 2 pi f c tau I. Remember, the flat fading channel coefficient H is given as A I, where A I is the attenuation of the ith path, e power minus j 2 pi f c tau I, where tau I is the delay of the ith path summed from I equals 0 to L minus 1. Now, something interesting happens, because now this delay itself is a function of t, which means I have to write this as tau I of t. Now, let us simplify this expression further in the next page. So, the flat fading channel coefficient now, when the mobile is moving, remember, with respect to the base station in the 3G 4G wireless communication system, becomes I equals 0 to L minus 1 A I e power minus j 2 pi f c. Remember, tau I is now tau I t, which is tau I minus v cosine theta over c times t. This is now equal to I equals 0 to L minus 1 A I e power minus j 2 pi f c tau I into e j 2 pi f c v cos theta over c times t. However, realize that f c into v cos theta over c, we have seen this before, this is simply the Doppler shift f d. So, f c into v cos theta over c, v cos theta over c is f d, hence this can be written as I equals 0 to L minus 1 a I e power minus j 2 pi f c tau I into e power j 2 pi f d t, where f d is now the Doppler shift. Now, look at this, earlier this was a constant with respect to time, now there is a factor which is time varying. So, this is a time varying phase. So, the phase is varying with time, which means the phase of every component in this flat fading channel is varying with time because of the motion between the mobile station and the base station, which means the whole channel is now varying with time, which means this is now not simply h, but this is h of t, which is a time varying channel. So, what has Doppler resulted in? Doppler, which is caused by the motion between the mobile station and base station, has essentially resulted in a time varying channel. Hence, let me summarize that observation over here. The Doppler shift or Doppler implies time varying In fact, we said earlier that the channel is a constant, but now however, because of Doppler, because of the relative motion between the mobile station and the base station, my channel has acquired a time varying character. So, the Doppler frequency shift is essentially resulting in the time varying nature of the channel. Thus, mobility results in Doppler. So mobility results in Doppler, which in turn results in a time varying. So, mobility results in Doppler, which in turn results in a time varying channel. And this is also known as time selectivity, time varying channel, also known as technically as a time selective channel. Remember, if a channel is varying in time, it looks something like this is the channel coefficient, it is varying with time. So, as time it is varying, which means it is a different time, it has different value. So, it is selective. Remember, we saw earlier frequency selective, that is if it is varying in frequency, that is at one frequency it is flat in the coherence bandwidth, but outside that it is varying in frequency, hence it is selective in frequency. Now, we are saying in the case of Doppler, which is there is something that happens similar in time, which is it is varying in time. So, it is selective in time. So, a time varying channel is also known as time selective. Let me summarize that over here. This implies essentially time varying essentially implies time selectivity. So, Doppler variation in time or Doppler in time results in a time varying or a time selective channel. Now, let us consider another, let us consider what is happening to each coefficient. Let us look at what is the relation at each coefficient. Let us look at a I of t, that is given as a I e to the power of minus j 2 pi f c tau I, all right, into e power j 2 pi f d of t. So, this was the flat fading coefficient earlier. Now, it is varying with respect to time. The varying factor is e power j 2 pi f d t. Now, let us look at t equals 0. At t equals 0, this is a I e power minus j 2 pi f c tau I times e power j 2 pi f d t, which is e power j 2 pi f d 0, which is 1. Hence, at t equals 0, a I of 0 is simply equal to a I e to the power of minus j 2 pi f c tau I. Now, let us look at what happens at t equals 1 over 4 f d. A I of 1 over 4 f d equals a I e to the power of minus j 2 pi f c tau I times e to the power of j 2 pi f d 1 over 4 f d, which is equal to a I e power minus j 2 pi f c tau I into 2 pi f d into 1 over 4 f d is pi over 2. So, this is e j power pi over 2, which is nothing but j a I e power minus j 2 pi f c tau I. Now, look at these two values. If you look at these two values at t equals 0, it is a I e power minus j 2 pi f c tau I. At t equals 1 over 4 d, it has become j a I e power minus j 2 pi f c tau I. So, it has changed drastically. For instance, if a I is real, at this point it has changed to j I a I, which is an imaginary number. So, the phase and in fact, the quantity has changed drastically in 1 over 4 d. So, similar to what we did in the context of coherence bandwidth, we can say in t equals 1 over f d, in time interval equals 1 over f d, my a I of t is changing drastically, or in other words, the channel can be assumed to be constant in one interval of t equals 1 over 4 d, and then it is changing in the next interval of 1 over 4 f d, and so on and so forth. So, we can say it as the channel is changing after every 1 over 4 d drastically, or it is constant over every interval, approximately constant over every interval of 1 over 4 f d, and this is known as the coherence time. So, coherence time equals T c equals 1 over 4 f d, which means the channel is approximately constant in this interval of length 1 over 4 f d, that is 0 to 1 over 4 f d. In the next interval of 1 over 4 f d to twice 1 over 4 f d, that is 1 over 2 f d, it is changing. Then 1 over 2 f d to 3 over 4 f d, it is again changing, and so on and so forth. So, if I look at the channel and if I take time in 0 to 1 over 4 f d, it is approximately constant. In the next interval 1 over 4 f d to 1 over 2 f d, which is of duration 1 over 4 f d, it is again approximately constant, and again in another interval of duration 1 over 4 f d, it is approximately constant, and it is changing from interval to interval. This interval of duration 1 over 4 f d is known as T c equals the coherence time. Remember, coherence bandwidth is that bandwidth over which the frequency response is approximately constant. Coherence time is that time over which the channel in time is approximately constant. T c equals coherence time equals time over which channel is approximately constant. right. So, Tc is the coherence time over which the channel is approximately constant. So, at this point let us end today's lecture, and we will take up this discussion about coherence time in detail again starting with the next lecture. Thank you.